Okay, we will start today's lecture with a demonstration on a PC. Last class we discussed some phenomena of electromagnetic, a magnetic circuit, and you know that these are can be obtained by solving the field equations. Now nowadays there are large very high speed software are available from which you can solve these magnetic circuits through a method called the finite element method, where they solve it for small geometries by creating some small meshes. They process the data, and we have used one such commercially available software to look at the magnetic field structure in a simple U-type electromagnet. Okay, and so we have basically worked out that U-type electromagnet with mild steel bar and also with Alnico bar, and you will understand Alnico bar has a different properties in the circuit because it is a basically hard magnetic material. Okay, and by using those material properties in the computer program, we can get a different type of flux pattern. We will see how it you get those patterns. Okay.
So this is the U electromagnet.
Yeah, it's okay. I'll explain. Okay. Yeah, I'll throw it. Okay, you can. That's okay.
The lecture started. We are not getting any transmission there.
Okay. Yeah, you go to that. Now, anyway, I will show it on the transparency also. So this is the U-type electromagnet, and this is the material. You can get the flux plot as you get it. Okay, I'll show it. So you will this is the electromagnet, and this is the mild steel bar. Okay. Quickly. I mean, in fact, here the flux plots are obtained from the computer, and you will see both the leakages here and as well as the fringing. Okay, when this is the bar is shifted to the left, I mean, you will notice that there is an asymmetry, and you get these results. Okay, are you getting it there? Okay, so you will see that this is symmetrical. So if you look at, if you can on the computer screen, you will have the main flux, you also have fringing flux, and you also have a leakage flux. Okay, and they are all obtained by actually solving these equations for a symmetrical thing. Okay, next one, if you shift it to anyway, I am projecting it here. No, this is not symmetric. That is displaced to the left. That means the bar is displaced. Okay. Again the same structure here. You displace to the left. Huh? I think we should have stored it. Oh.
Now there is increased number of equipotential lines.
Okay.
Earlier there were 20 lines, now there are 30 lines.
This is again not symmetrical. This is the bar is displaced to the left. Okay. Now you will notice that there is an asymmetry on the flux lines as you saw here. Okay. And again you find a different type of fringing patterns. There is, because when it is bar is displaced to the left, the fringing pattern changes, and these you also have the leakage paths.
Does the fringes increase or decrease towards the
Yeah, one side. Okay. Yeah, and what you are seeing is here. Whatever is on the screen is here. Okay. So these are the when the bar is displaced to the left, so you will find a different type nature of fringing, and the flux patterns will change. Okay. And next we will show the effect of, instead of replacing with a mild steel, you will have an Alnico bar. Okay. So if you put an Alnico bar, okay, this is the pattern. Yeah, in between there is an air gap. So here is an Alnico bar, which gets magnetized. It is aiding, because it is also storing magnetic energy, and therefore it is aiding electromagnet. Okay. That means whatever flux that is coming here is aiding. The MMF here aids this. Okay. Because you are having a Alnico bar like this. Okay. Yeah.
Sir, on the top of that bar, sir, that picture is not clear, sir.
No, that is just a distortion, but this is a total U type electromagnet. Okay. And this is a bar. Okay. And you will notice the actual flux patterns, how the fringing takes place here, and also the leakage fluxes around here. Okay. Then we have another, which is Alnico bar opposing the electromagnet. So if it is magnetized in the opposite direction, you will see that the overall fluxes will be small compared to the situation where it is aiding. See, this is aiding, there is more flux because this is polarized in this fashion, and this is when it is opposing. So I mean this is just to give you an illustration how the flux pattern actual situation will change depending upon the magnetic circuit. Okay, both with mild steel bar and the Alnico bar. Okay, has it come in the? Okay. So those who can see on the screen, this is the opposing. Okay. This is the one where opposing the electromagnet. Okay. Do you get the one which aiding?
So please do it on transparency.
Okay. So whatever is on the screen is on the transparency. Okay. So this is just to give you a sort of illustration of how the actually flux lines will be there as calculated. Okay. Okay, we'll stop it here. Okay. And what if anybody interested? It will be same thing can be demonstrated in the laboratory later. Okay. And the pieces will be shifted, and you can see it at. In fact, we have done it for several different geometries, and that can be used in the package. Okay. Now, last class we also discussed about some of the curves. I thought we can, before we start today's topic, I want you to have a little feel of the some of these curves. Okay, this is the magnetization curve of Alnico 5, okay, which is used as a permanent magnet. Okay, and these are the BH curves of selected soft magnetic materials. These are BH curves of different materials, and while you are doing the calculation, you can use these curves. For the given B, you can find H, or for given H, you can find B for the appropriate materials, and then do the calculation, because this takes care of the non-linearity in the circuit. Okay. This is a DC magnetization curve of one of the materials. It's called a M5. This is one of the trade names, M5 grade silicon steel. This is the magnetization curve of these materials. Okay, and these will be made available to you so that you can use them for any of these calculations. Okay. This is the BH curve of M5 when you are going through a hysteresis loop. The same material, okay, for different type of maximum flux densities. Okay, if you go to higher one, that means you will have loop inside the loop. Okay, this is again one of the BH loop or hysteresis loop for one of the material called delta max material. But it is one is with low frequency or the DC if you go through, and if another is a high frequency. So you will notice that the hysteresis loop is also depends upon the rate of change of these. That is it is dependent upon the frequency of excitation. Okay. Okay. These are the DC magnetization curve for common permanent magnet materials. So last class we discussed that there is a improvement in permanent magnet materials, and this is the latest one, neodymium iron boron. So this material uses a very high energy density, and whereas the old ones, Alnico etc., they operate at very low BH density. So so these improvement in materials have made the improvement in permanent magnet devices. Okay. Okay. Now these are just some of these characteristics which will be made available to you, and for this will be most of the designers use these calculations for any magnetic circuit designs. Okay. Okay. Now let us start with today's topic on AC excitation of magnets. Supposing you have the same type of electromagnet, but instead of DC, there is an AC. So here excitation is AC. Okay, and we can expect that when the excitation is AC, what will be the flux also? That will also expected to be AC. Okay, this is the flux, and when the flux is changing with time, then what do you expect? There will be an voltage induced here. This has N turns, and you will see if flux we can say is phi max sin omega t. Okay. Then we have defined the E as in the same direction, N d phi by dt, and you get this as N omega phi max cos omega t. That will be the E. So if you plot a waveform, you have phi, and the E will be cosine function so this is the voltage E. And what is the peak value of E? Is N omega phi max. That is the value of the peak of the EMF induced. Okay. So now to produce this phi, this current I is producing phi, isn't it? And naturally I and phi must be in phase. Okay. So let us say that this will be I, right? So I is producing phi, and phi in turn is inducing a voltage E. Now if you neglect resistance, E opposes V. Okay, E opposes V. This is in the R, that means V minus E is 0 or V equal to E. If you neglect the drop in the resistance. Okay. So whatever you apply a voltage, it is automatically opposed by an induced voltage, okay, to make the circuit law valid. And the current will be drawn to produce an MMF which will produce the flux at each instant of time. Okay. So this is a different phenomenon as in unlike in a DC, where in a DC current is decided by V and R basically in a DC. Okay. In AC that is not what is happening. This is a slightly involved procedure. So we have three waveform I, phi and E here. Yes.
is greater than 5 m.
N omega?
5 m.
Yes. This is E in volts. This is 5 m. Okay. And they are not to scale. Okay. Now if you look at this, you can draw their phasor diagram. Okay. Supposing you have the E phasor, where will be the phi phasor? Huh? So the phi phasor would be lagging and I phasor would be same with E. Phi phasor is so you notice the following. What do you notice here? So I lags E by 90 degrees or phi lags E by 90 degrees. Okay, it's very simple. So you get a simple. So whenever you take an AC system, ideally the current drawn would lag the voltage by 90 degrees because this is taken as an ideal core. Okay. Now, what is the voltage induced? This is the voltage induced instantaneously. So what is the RMS voltage? Will be omega n phi max by root 2. That is omega is 2 pi f n phi max by root 2. Okay. And the 2 pi by root 2 is 4.44. Okay. So we have a standard expression for E RMS is given by 4.44 f n into phi max. This is a very common expression which we also use it in transformers. Okay. So whenever you have an voltage induced is related to the flux by this expression, where f is the frequency of the oscillations and n is the number of turns of the windings and phi is the maximum flux. Okay, that is phi max. The phi is, this is the phi max. This is the maximum flux and this is the maximum voltage and this is the maximum current. Okay. Is it clear at this stage? Yes. So it's very simple. Now, ideally we have this type of a situation, but we can also see that if there are any practical limitations. Okay. Some of the curves which I had just shown you, the DC magnetization is therefore different than AC magnetization. Okay. And therefore we can also write a relation between I and phi, a BH relation in AC. which is not, may not be same as DC. Let us see how it we get such a relation. So we can write I as root 2 times I max, maybe sin omega t. I RMS. Okay, and what will be HRMS? That is RMS H is also varying. Okay, so that will be number of turns into by the length of the core. Okay, because with sinusoidally varying I, H also will vary sinusoidally with time at all points in the core. Okay, and what will be B max? V is phi max divided by A, where A is the area of the core. Okay, and length is LC. So we have a length L and area A, and we have HRMS and B max. Okay, right. Now we also have a relation. The phi max is equal to ERMS over 4.44 into F into N. Okay, we have the phi max and we have okay, so IRMS is HRMS LC by N. Okay, now tell me what is what will the product of ERMS into IRMS? No, E and I are at volt amperes. Okay, so please find out what is ERMS into IRMS. See, in terms of HRMS into B max, please find out. I want this in terms of HRMS into B max. See, ERMS is equal to 4.44 Fn into phi max, okay, into IRMS is HRMS into LC by N. Okay, but phi max is A into B max. So this is equal to 4.44 Fn B max into A into HRMS LC by N. Okay, so this will be equal to 4.44 F into A LC into B max HRMS. This is ERMS IRMS. So what will be this? What is A into LC? Is the volume, and this is for a given frequency. So that is 4.44 F into volume into B max into HRMS. Okay, ERMS, IRMS. Now this term is called RMS AC volt amperes. Okay, this is called RMS volt amperes. Okay, and you will notice that RMS volt amperes is equal to a constant, is depend upon frequency and also depends upon the product of B max into HRMS. Okay, so it will be 4.44 F into volume into B max HRMS. Okay. Now, per unit volume, you can find out the RMS volt amperes for different operating B. Okay. So these curves per unit volume for the material is specified. That means as a function of B and H. For the operating B, you can find out what is the RMS volt amperes per unit volume. So using, there are curves giving volt amperes versus B. Okay, operating for the given frequency. Okay, I will show you the RMS volt amperes for one of the materials here. These are called exciting RMS volt amperes. Okay. This is the exciting RMS volt amperes per kilogram at 60 Hertz for a M5 grain oriented electrical steel of this thickness, 0.03 centimeters thickness. Okay. So this is a curve which can be used. So what you can do is, it gives you the on the x-axis RMS volt ampere per kg for different values of beam. So in the y-axis you have the B max in Tesla. So if you know what is the B max in the core, if you want to operate the core, supposing this core at a given B max, then all you have to do is to find the RMS volt amperes from this curve, multiply by the volume. So it will give you the total RMS volt amperes. Okay, and then you can find out the exact current that will be required to produce. So what will be the IRMS? If you know volt amperes, you know the voltage, you can find out the current drawn, magnetizing current drawn for this. And this current that is drawn is called the magnetizing current, exciting current. Okay, so you please note down. So from the RMS VA using the curve, we can estimate IRMS for given B max. if you say you would like to have a Bmax of say 1 Tesla, you can use these curves and get the IRMS. And this RMS it is named as a magnetizing current. Okay, often it's also called, so this even sometimes they indicate it as IM. Okay, so this IM lags V by ideally by 90 degrees. Okay, and IM depends upon the material property. What will be IM if it is having very high permeability for a given voltage? What will be the magnitude of IM? Can you guess? So if it is a very good material, okay, if mu is very high, then IM is low. Okay, so that means you note down that high mu causes low IM, right? So if you make a non-magnetic material, so it will draw more current. That means ideally, if mu is infinity, then IM is 0. Okay, it should not draw any current whenever it is very large. Okay, because this has relation with the beyond edge. So now we have a AC magnetization, which is in contrast to the DC magnetization. So this you don't use the DC magnetization curves, but you use this AC magnetization curves. Okay, and that is frequency dependent. You have found the IRMS for the given E. Okay, you have now for a given E for this AC circuit. Now what is the ratio of this? What is its unit? Yeah, but would you like it a resistance or reactance? So this is called XM, or the magnetizing reactance. This is called, that means the coil reactance is given by this. Okay, so this will be equal to omega into Lm. Okay, Lm is the magnetizing inductance. Okay, now this is maybe different compared to a DC inductor. Okay, because of non-linearities associated with it. Okay, so this xm will be omega by root 2 n into phi m by im, because it is the ratio E is 4.44 Fn phi. Okay, so we have a relation, xm is given, is proportional to phi m by im, and inductance L will be n into phi m by root 2 im. So the maximum flux density to RMS, this is the maximum flux, and this is the RMS current. Okay, this is maximum flux and this is RMS current. So you have this you can call it also as an AC inductor. This is an AC inductance. So we now define the AC values. Okay? Yeah.
So why are you saying that ERMS by RMS is reactance? Can't it have a resistor component?
Wait, I didn't find, we have neglected all resistances here. Okay? We are not taking, let's come back to resistance later. So it's an ideal situation in AC where there is no resistance in the winding. So your coil works as a pure inductor because that is producing the flux. Okay? This has a property of an inductor, and in AC that inductor is producing the flux, and the flux is producing a voltage, and voltage by current is a reactance. Okay? So this is one phenomena that you see in AC. So in AC you find a back EMF. That is phenomena number one, okay, as we have understood. Let us see if anything else happens in AC. Can you tell me anything else happens? Okay, so you have learned that there is something like a hysteresis effect. Okay, and you are told that whenever you have you start increasing the current, it will also result in the flux changing, okay, and you are told it will go like this, okay, typically from 0 unexcited to a given position, and then it will also cause an instant E, because whenever there is a flux there is also an E, okay, and the energy input from the source is what? Let us say in time dt, energy input okay, let us say W field or dW field is EI into dt, is it right? So this is an energy is going into the magnetic field from the source. So source is giving some energy into the magnetic field given by EI dt, okay, and this is nothing but E is N d phi by dt into I dt. So it will be Ni into d phi. Okay. So Ni is what? MMF. So let us say F d phi. Ni is MMF total, so it is F d phi. Okay. Or you can also write this different ways. So dW field will be F d phi, or this is equal to N or I d lambda. That is, if you change lambda by increment d lambda, So there is a change in the field energy. Or if you are changing, let us say you are changing from 0 to some specific value I, okay, I mean because this can be E, phi or lambda, they are all linearly related, and what is the total of, supposing you want to increase from 0 to I and goes to some value, let us say lambda, okay, I would say lambda star, let us say I star. So I have changed the current from 0 to I star so that the flux linkage changes from 0 to lambda star. So what is the energy stored? W field will be integral dW field from 0 to lambda star, okay, or that is integral I d lambda from 0 to lambda star, okay. So what does it indicate? Huh? So this is the area to the left of the curve. Left of BH curve. This is also a sort of a magnetization curve. So this is the stored energy. Okay. Now with this fundamental principle being understood, that the energy that is stored or into the magnetic circuit in the process of exciting it from a 0 flux to a given flux phi star or a lambda star, certain energy is taken from the source. Okay. Now if you have B and H, okay, you are saying that in the process of lifting magnetizing it, certain energy is taken from the source, and we also know if you retrace it back, okay, if you retrace the current from, this is I up to, let us say you go to its maximum value and it reaches the flux B max, okay, then if you go from I max to 0, you know in the process, because you are exciting the current by an alternating current, okay, this is I max, okay. Now 0 to I max you are gone and I max to 0 you are coming, but then it is not retracing the path, right, and that means it has taken some energy. It is not, the return, it is not giving back the same energy to the source, okay, and then if you go back like this, so you are told it retraces this path, okay. So when you have an I which is changing from plus I max to minus I max, okay, this is I max, this is minus I max. So it will retrace this path going from plus B max to minus B max. This is minus I max. Okay. So the hysteresis process is that the energy that is taken from the source, it is not returned to the source. So in each cycle certain energy is retained by the circuit at each cycle. When it goes through one cycle, okay, so we can say that at each cycle energy is retained by the core. So this is what we observe. Energy is from the source, it takes some energy. In each cycle it is not. So that means for each cycle it does. So for per second, if it is a 50 hertz, 50 times that energy is retained. Okay? That means there is this energy that retained per second is called, what do you call this as? Hysteresis loss. So we define hysteresis loss is energy per second. This energy lost per second. That means it is not returning to the source. Okay? And we can, on what factors does it depend upon? It doesn't depend upon the attendance. It depends upon the maximum flux density. Okay? And it depends upon the frequency. Okay? So I'll write to you the formula that is used. The P hysteresis is some constant C1 into F into B max to the power of N. Normally N is typically 1.6 to 2.5. And this N is, is called a Steinmetz's constant. pH is the hysteresis loss. N is a exponent, B to the power of N. N is typically 1.6 to 2.5 depending upon the material. Now the area of the hysteresis loop decides the loss, and the more maximum value you will go, the loss will be more. So because the hysteresis loss, you can have several loops like this. Okay? So this is a phenomenon which you are supposed to know, and next class we will look up the another phenomenon called eddy current loss. Okay? Yeah, I'll take the attendance.